we're good to start. Right. So then, go ahead. Yeah, let's start. Okay. So this talk is, primarily motivated by combinatorics applications, but it's eventually going to be an application of communication complexity in the field of combinatorics. And this extends the line of work that has been quite influential in additive combinatorics. So it starts, actually, interest in this problem started in, well, probably before, but the first major result was in 1927. So this was when Van der Waerden proved quite a brilliant statement. What he said was, if you take a large enough n, so all n greater than some value, if you split the numbers from 1 to n into C disjoint sets, then there will exist one of these sets where there is the SI, such that SI contains a k-length arithmetic progression. So you give me your C and K, I will give you a large enough NCK. So if I take any n larger than that and I split it up into C sets, at least one of these sets must contain a k-length arithmetic progression. This was proved in the style of Ramsey theory, where you make n really large with the pigeonhole principle multiple times in various ways. And so it's a great result in Ramsey theory, but in additive combinatorics, for instance, this doesn't really tell you much about this problem. So the problem here is you want to know what is the largest subset of 1 to n, which avoids the creating. So this kind of morally says that you can't have a very large set if you have a very large set in 1 to n that contains the 380. It's morally against the statement. Or sorry, that avoids 380, it's morally against the statement. Because this is saying that you will find one of these sets containing a k.
So the difference is that there you might be using the fact that it's partition, and not just that the fact that one of these sets is large.
Yeah.
Right. So somehow the bottom follows from the top. Did I get it correctly?
The bottom follows from the top.
I mean,
you say that.
C.
Right. So if you show that RTN is small, then it implies that C has to be large.
Right.
If you have a small set that avoids the edges, that kind of implies that you need a lot of partitions. So that
I think it's the other way around.
okay, so suppose that there is actually a large set that avoids the negating. We can use that set as S1 here. Right? It's fine, S1 doesn't contain a K, but it says that among n minus S1, it's saying that this is now what's hard to parse. Right? So it's kind of avoiding saying that there is a large, that every large set contains a KP is not yet implied by the set. There can be a large set avoiding a KP, but then the rest of it must contain one of the set. There should be a set there. Okay.
Oh, but if R3 is less than n by C, or n by C minus 1, right?
Right. So R3 cannot be less than n by C. That is the set that is. Because if R3 is less than n by C, it's saying that every set of n size n by C contains a KP. And then
No,
why is that problem?
no, one of these sets will be an set n by C.
So just say that. Suppose R3 of n is equal to n by c.
Then it follows that, if you break n into c pieces, there will be one. I mean, the bottom one will follow.
Then the bottom one will follow that. So that's this way. C and because no matter how you split it, there is a large set, and therefore that cannot avoid it. It's larger than this.
Right.
So it can be
You push things like this. I mean, right, and I guess what I'm asking is that what you can prove about R3 isn't strong enough to imply what the bottom. No.
what we can prove with R3.
So the known upper bounds on R3 are strong enough to imply when the variance. I guess.
Oh yeah, the known upper bounds are strong, but we haven't gone into what those upper bounds are yet.
Sure.
Yeah.
Yes, sir.
This is for all partitions.
Yeah, this is for all partitions. Any partition, they will exist at some point. And the language that we'll be using to create this is, instead of calling this partitions, we'll be coloring the elements of 1 to n with C colors. So each color defines one of these sets with the number of things colored, the first color, second color, and so on. So we'll talk about coloring instead of partitions. It'll be easier later on. But this is like right at the beginning of 1937. So in 1936, Erdos and Turan decided to study this problem specifically. And this was like back in the day when you could just take upon maths.
So are they getting bounds on NCK or on?
So the NCK bonds are like really bad. It's practically.
No, this 20 gram that was giving bounds on NCK or?
No, it was saying that there exists an NCK. For all CNK, there exists an NCK. That's the all right, so now we come to 1936 when Erdos and Turan they initiated a formal study of this one. What is the largest subset of n that actually avoids the APs? And what they were able to prove is that R3 of n is less than equal to say 4 by 9 times n. And on the other hand, they were able to they referred to a result by Zechariah, which says that this is actually at least polynomial. You can find a set of basis ones that does actually avoid the APs. And we can actually see this quite easily. So let's take the question. Yeah. So what is the meaning of 0 dot 3 for this? Oh, this is the log of 3 base 2. Right, so it's just let S be equal to all of the x and n, such that if you write x in its ternary representation, so base 3x contains only 2 of the values. So say it contains only 0s and 1s. The claim is that this set is free of creates, and it's fairly easy to see this. Suppose that there actually is a creating. So there's a plus d and a plus 2d that are all in this set. Let's just look at the smallest digit in it. If that digit is 0 in the first one, and if it's 0 in the second one, then it must be 0 in the third one, because you're adding the same difference. If it was 1 over here and 1 over here, it must be 1. But if it was 0 and 1, then it must be 2 here. It's 1 or 0, it must be 2 here. And this is the least significant digit, even for everything like this. So it's so if it's the first case, if it's 0, 0, 0, then you look at the next bit, this could be 1, 1, 1. That's the case, you look at the next bit. The first time they're different, that will show that a plus 2d does not belong to S. And if they were never different, then a and a plus d are actually the same vector, and they're the same number. because they're the same in every coordinate, so that's not actually the case. Okay, and the size of this, if n is 3 to the d, then the size of this is 2 to the d. So that's poly n, that's n to the 0.63. And we'll write this in a different way in terms of density. The way we're going to write this is n into the power, n into 2 to the power minus 0. And there's a reason why we're doing this. So this is like the full set n, and this is the density of the set written in the exponent. This will be very useful to us, and we're going to say this. It will become clear later on why it's useful to us. So right, the question is it actually minus 0.37 log n, or is there a smaller constant that you can put here? So if it goes down to 0 log n, that means linear. If it's delta log n, we have 2 to the minus delta log n, that's the same n to the 1 minus delta. So they conjectured in this paper that this should actually be the correct column because you can't think of anything better than this. But a weaker conjecture could be thought of as saying if you write it in this format, delta is a constant larger than 0. So it's bounded away from n polynomially. And it turns out that that is not true. So that's our next result here, 1942. Salem and Spencer. Salem and Spencer. It's not me. They showed that, right, that there actually is a set whose density is like 2 to the minus log n by log n. So 1 by log n is smaller than any constant, so that's very close to linear. So that was Salem and Spencer. Then it was improved by wherein, and this is going to be quite important for us. So I'm going to spend some time on this below. What he showed was that you could actually improve it all the way to minus order square root of. So that's much better than 1 by log n. That's divided by x squared. And the observation behind this was actually pretty neat. So assume that instead of numbers here that were in an AP, we're actually asked about vectors. So suppose instead you were looking for S that is a subset of q to the d, and we're trying to avoid vector 3 APs. So that means we're avoiding things of the form v, b plus w, and b plus 2. If this is the question, then there actually is a very nice way to do this, which results in a quite large set size. And it's really simple. So if we define S R for R, that's not just R, say M. Sm are all the vectors such that the norm of the vector squared is equal to n. So every vector in a set Sm has the same vector. Then the claim is that Sm is free of fields. And the proof is quite simple. It's just basically a higher dimensional version of you can't have 3 points all on the same circle. 3 points in a line all on the same circle. Every line intersects the circle in only 2 points.
This relation is mod q or
No, this is not mod. This is just in natural numbers. But we know what value this can take. M is between 1 and q squared d, q squared for each coordinate and the plus c coordinates. So that means that there actually is a set of size at least n by q squared d, where n is q to the d, which is free of these. Now we can manipulate q and d to make this optimal. But unfortunately, this is not what we're given. We're not given vectors, we're actually given integers.
But can you represent them in binary?
Right,
Leaving
so
some
binary,
for the carry?
so this is exactly what wherein tried to do. We took an integer, trying to represent it as a vector, and then saying integer addition is the same as vector addition if I do this transformation. And so avoiding integer is the same as avoiding vector is.
Using some kind of from and G to and yeah.
Oh, no, we were still sticking with the same n, but we want to represent it in some, yeah, we will want to represent it in. That's why I showed the q to the b here. So we'll, for every integer, we'll take its base q representation. So let n b choose q and d such that n is at most q to the d, and then take the base q representation of the integers. Each integer has been transformed into a vector. But there's one small problem with this.
Carry.
Yeah. So if I take, say, the number 39 and I take 42, if I add these two, I'm getting 81, but if I add them in vectors, I'm getting 7. So if I add them as vectors, I'm getting this. If I add them as integers, I'm getting this. So there's a problem here. So what do we do? So wherein the idea was basically this.
You not just leave enough room in the representation to store the carry,
To store the carry.
like you represent it in base, right? The carry is that true? The carry is either 0 or 1.
In the case of PHP, the carry is always everything. Yeah, we will go to higher, longer ages later. For now.
No, I guess what I'm saying is that like 39
Yeah.
is represented by the number 0309,
Oh, okay.
where I guess the 0 should just be binary. So you're using this kind of mixed encoding where some digits would be binary and some digits would be Q area, I suppose.
Okay.
And now you have one binary digit for each Q area digit. And that can store the carry down, I guess.
Okay.
That works? Maybe.
Well, so if you have, so if I take 39 and 40,
Maybe it's not.
I'm writing it 0309, 0402. If I add them, I'm getting,
But now you have,
I'm getting 07 and 11 as vectors.
yes, you have to account for sets that include points that have the carry bit already set. Right? That's why.
Well, it is something along this lines, but this doesn't quite work because
It's too much
I'm
space.
supposed to be getting 0801 in my integer addition,
Oh,
but I'm getting 07. But we will want to restrict ourselves in some way, and that is what wherein does. So S is, so let's start off by just defining an S, which is every number in n, such that if you look at the vector form of the number, so let's call this implementation. If you look at the base q comma d notation of n, this only has entries. This is a subset of n. You've lost a lot of n subset of n. You've lost a lot of integers, but now you're left with integers, such that if you add them and you get another integer in here, you're sure that no carry has happened. Basically saying that if I take 34 and I add 42 to it, whatever answer I get, either it's not in the set S, but if it's in the set S, then I know it's happened as vector addition and there hasn't been any carry.
This is similar to the air strong.
The Erdős idea, Well, the Ehrlich idea, yeah, I feel like it's similar, but there's something missing after that, I think. Like this step might be somewhat similar.
Yeah, I mean, just the slide,
Yeah.
just that, the idea that since you have no twos. Everything is, there is a block map, and then this one's like a multi-dimensional version, and it does this many.
Yeah, but this doesn't avoid, yeah, so there's one sense in which this has avoided PAVs, but it's not yet really done that because you can easily find PAVs
Yeah,
in which
right.
all the entries are smaller than 2.
Yeah, if it was all zero, yeah.
Yeah.
Because there's many entries in system,
Yes, exactly, because there's many.
but that's from the secondary.
Then now you define S M, and basically the subset of F for which the vector has length n. And you know that Sm is actually PAV3. That's integer defined, not just the vectors. Okay. So this is where the idea we want to check. Okay, so how much have we lost here? So we haven't yet set our Q and D, we're going to need to optimize this. So the size of S divided by N is equal to 2 to the minus D. For each dimension, I've lost half my inputs, so it's still minus D. Then the largest size of Sm divided by size of S is at least 1 by Q squared. So the eventual set that we get, which is Sm, has size n times 2 to the minus d times 1 by Q squared. Now, so we want to maximize this value under the constraint that Q to the d should be at least n. How do we do that? So first of all, we have a 2 to the minus d here, and we have a 1 by d here. So just for simplification, let's assume that this d wasn't there. This is what's going to cause the main degradation in d. What we would want to do is we would want to set d to be approximately equal to. So we want d to be approximately equal to. And let's actually write it down. Minus. And if we want this to be maximized, we want d to be approximately equal to log of Q squared. So that means but at the same time, this value we know that m must be larger than Q to the d. So if I multiply these two values, the times log of Q squared is equal to log of Q to the 2d, which is at least log n squared. So now I'm reducing it to question A into B is equal to some known value. So let's call that C. And I want to minimize A plus B. So this will happen when I set both A and B equal to square roots. Like the extremes are I set A equal to C, B equal to 1, in which case A plus B is C. The middle places where A and B are both square root C, in which case the sum is twice of square root C. So if I do that substitution, both of these I'm making it square root C, which is square root log n squared. Then I get n times 2 to the minus twice of log square root log n squared. So because I've made some approximation here, D and it's not actually 1/2 squared, it's 1/2 squared D. There would actually be a like a log n term. But we'll be ignoring that. It's very good for the R3 of n. That was technical part number 1. There's not really that many technical parts. So this was wherein showing that there is a large set. Then in 1953, Ross made a breakthrough. He showed that R3 of n is actually smaller than when he showed us like order n by log n. So that was 1953.
Who is this you said?
Ross. 1961 is another important thing, but we won't go into the details right now. This is Rankin, who looked at the analog of this, but with larger, with K. Basically, he looked at the quantity RK of n. What is K is. And what he showed was that RK of n would be equal to n times minus. Again, there's some constant over here, depending on K. Then this, as K increases, it should be easier to avoid K's because K's are longer sequences. And he showed that actually, yeah, it is easier to avoid K's. And for example, if K is 1,000, you just have the 10th root of log n instead of square root of log n. And then finally, there's similarity theorem here, which shows that in fact RK of n equals small. That should be obvious, right? No, it's easier to avoid this, so it's not an obvious. If you're going to avoid this, your set still needs to be something.
Oh, you're saying, not for K, for anything.
For any case, this is similarity theorem. But after this, Green and Tau also proved that if you just restrict yourself to primes, the set of the primes also contains arbitrary large arithmetic variations, even though that it's not big enough to fall into this linear category. It also affects arithmetic variations. And that was important enough to be put on the walk in campograms. If you look at the tiles of mathematical progresses, Green and Tau.
Really? What?
So if you walk along the park, there's lots of tiles in the ground in various, like Euler, Euclid.
I've never seen it. Okay. Well, there you go.
since then, people have tried to improve the other side. So showing large sets exist is like constructing large sets, but showing that if your set is too large, it cannot avoid a KP. There weren't as good bounds on that, but recently there has been a lot of progress. And in fact, in 2022, a bunch of computer scientists were prominent for people wrote that RPLN is actually minus 9.
Oh.
This is a massive breakthrough that happened this last year. This was Omega Kelly Humans. So yeah, this is what's called the correct form in combinatorics. So they finally proved that this is the correct form. Like I think that improving 92, which is okay. So this is a history of finding AAP presets and how large their set size should be. Our talk is related to that, but that's not actually the main object of concern. It's going to be something closely related, which is corner presets. This is defined as the maximum size of the subset. That's that it avoids corners.
This bell.
No?
Alright, so.
So this not, it's a little part. This is how it's represented. It's not.
The upper ones are all probabilistic method. So,
The upper ones, like these ones.
yeah.
Oh, so it's a lot of, actually, it's not much probabilistic method. It's Fourier series and regularity lemmas.
What is going to say?
Yeah, so I didn't get it. All right, so what is a corner? So I can define APs as basically 1, 2, 3 is an arithmetic progression of cycle length 3. And if I call this set S, then any set of the form n plus b times s is also a 3-prime arithmetic progression. So I start with any number, and then I add 3 to it, add 2d, add 3d, that also defines. So it's basically, this is a set closed under translations and scaling, and it's generated by this one element, this one set here. So a corner in k dimensions starts with this set, the 0 vector, the origin, E1, E2, all the basis vectors. So it's a set of k plus 1 vectors. So in 2 dimensions, basically, it's this corner of the square. In 3 dimensions, it's the corner of a cube. And then you can shift it anywhere, you can scale it by any amount. So basically, these distances have to be the same. So the general format will be a vector v, v plus b times e1, b plus b times e2. This is a
question. Yeah. Seems like the K is in the K progression of the K corners are completely unrelated Ks, right? In a corner, a K corner has K plus 1 elements.
yeah, so that is an annoying aspect there. Yeah, but yeah, so the k here does mean k points in an arithmetic progression. The k here is technically k plus 1.9.
And in k dimensions is equals to one.
And then k.
Okay, so we shouldn't try and map those on each other at all.
We absolutely should. We will do that in a bit. Sure. So that's exactly what was done in 1974 by Oct-20 and Zemreni. So a lot of work had been gone into arithmetic progressions, which are one-dimensional. And Zemreni was interested in higher dimensional variants of the exact same question. And so they asked, what is the simplest two-dimensional shape? And they decided that that was in square. Turned out square is not the simplest one and way too complicated, so they're gonna have this, and now we have a corner. And there's a huge difference in what we can prove for corners and what we can prove for squares. Squares are really comparatively for some reason. But that's quantitative. Because in another sense, corners are all that you need. I'll explain why. What is? This. That's fair to what happened there. So over here in 1978, Kirsten, Berg, and Fats Nelson. In 1978, they proved the multidimensional Zemreni theorem using concepts in ergodic number theory, whatever that means. So what is a multidimensional Zemreni theorem? It says let F be any subset of any finite subset of z to the m. So it's some collection of points in z to the m. You can think of in the same way, you can think of this defining a pattern. So the pattern is anything of the form b plus d. Translate anywhere you scale by any amount. All the structures that you get starting with f as your generating set will give you the things that you want to avoid. And the theorem says that if you define a similar notion for R and M, is so basically, if I take a subset of n to the m of constant density, it will always contain a copy of this file. And this is like the mother of all such statements because it covers literally any pattern you can think of. Whether it's different translation and scaling. And it turns out that in order to prove this multidimensional Zemreni theorem, all that you need to do is prove that this value is small o n to the k for all k. So this thing is implied by for all k. Here and small o. Okay.
Just because you can show that there's lots of corners and then, okay.
So the idea is, this is some set with some finite number of elements. So whatever finite set that is, that's the k that you want to set. And then starting with that corner, you take a linear map that maps those elements onto it. So these are all independent points. So it might be an affine linear map because you have 0 here. But here you have k plus 1 independent points essentially. And you can easily find a map that maps it to any set F, with each one is done independently. And then you argue that if you have a large set here that avoids F, its inverse map in some sense is a large set that avoids corners. If I prove that there's no large set of avoiding corners, then that means there's no large set of avoiding. The corners is really all that you need. And so for this reason, understanding exactly how big a corners preset is became a very interesting question.
No, when you say it's all that you need, it's all you need to show little o, it doesn't mean that the asymptotics of corners, in other words, it's.
Yeah, no, it is. Okay. There, depending on what f is, you could have weird constants coming in. I'm not sure. Yeah, actually, I can't really comment on. But subconstant match to subconstant, that's
Yeah.
yeah. Also, what I said right now needs much more work to be made into it. There are some things that I just get like the dimensions being different. So in 2006. All right, so what else do we know? Since corners, if you show corners, you show it for everything, that means that we actually have a relation between corners and arithmetic progressions. So essentially, like this. So the density here that you need is always actually this is what Einstein's already showed back in like 1974, that if you have corners, you already have the result of arithmetic progressions. And it's just saying that it's easier to avoid corners than it is to avoid arithmetic progressions, because corners are complicated. And k minus 1 here, because if you have k minus 1, that's k points, and then you can map these k points onto a k length arithmetic progression. Yeah. So now you can ask, what is the largest corner preset that we know? This is telling you that every time you find the arithmetic progression preset, that automatically gives you a corner preset. And in fact, until very recently, that was the case. Every single large corner reconstruction that we knew was basically the arithmetic progression construction done for this mechanism. That changed only recently in 2021.
You mentioned the theorem was done the same time as the same.
So Semitic theorem was here, multidimensional. There's 3 years ago. Yeah, but it's not. So initially it was proved using this ergodic theory, and then later on it was proved combinatorially using higher dimensional Fourier analysis, which was like introduced for this topic. And Terence Tao claims that if you look at all the various proofs of the multidimensional Semitic theorem, it's like a Rosetta Stone, where you look at one field of mathematics, how 2 different fields of mathematics prove it, and then you can find a translation between those fields of mathematics and know this corresponds to that. And really, it's like a huge theorem. Combinatorics. So in 2006, 2007, they're basically quantitative, like better quantitative bound here, so we show that are I feel them for and this was by spread out, and then Timothy Bowers in general. Like inverse after members. Basically, it's barely better than saying it's still constant.
Hopefully.
In first step. It's extremely slow right motion. I think that's.
But in 2001, there was a construction part of reset that would be a different method, right? You said in 2021, right?
Right, yeah.
There was a different kind of construction. Oh, we're gonna touch on that, we'll read that on.
No, that's what we generalize down here, so
Oh,
we're going to go deep into that. And then anyone? We know and spread it on. So initially, the best known two-dimensional quadratic set basically has the same density as this. So we had R3, this would be R2 corner line with the include, with there is a better set where its density is 2 to the minus 2, but it will be a lot easier. It was improved from 2 to 2 square plus, which is something like 2.8 and this is something like 2.4. So prior to this, there have been improvements to this quantity beyond this, but actually I couldn't put it that way. Prior to this, there have been improvements to this quantity, which is why there were improvements to this quantity. But all those improvements were in the small order terms. So this is the first improvement to this quantity in this highest order term. Then a couple of months later, Green improved this result further in the same way, except that it's 2 to the minus twice the log of 4 by 3. This is like 2.8 square log n, this is 2.4 square log n, this is 1.8 square log. And in our work, what we do is we get rank interval, which is the K equation. And it's along the same lines, but we have to do a lot of work to get there. We show similar improvements that this order K term, whatever that constant is hiding there, that constant can be improved. And exactly the same in previous times, this quantity has been improved in the small order terms, but now we're improving this quantity in the largest order. This is the jump part with Diana Hamiltonian, Tony Tassi, Morgan Shirley, and Ali Schrader. Okay, so where does communication complexity come in? So also linear algebra also use communication complexity to get this improvement. Green later wrote a paper saying you don't need communication complexity here, the combinatorics to this value. And then we wrote a paper saying communication complexity is the use of the improve this as well.
With upper bounds or lower bounds?
Sorry.
So are you going to use upper bounds in communication complexity or lower bounds?
So these are all constructions of large sets.
Sure.
We're constructing better.
Okay, cool.
Okay, great.
Is there a Rosetta Stone for this communication complexity and whatever Green did in the next paper? Because we're saying that, well, at least,
Mostly
you see what I'm asking, right? Because apparently,
on the lower one side, there were the techniques that were being related.
no, but I'm guessing like Green used some technique to prove his.
Oh, yeah, absolutely. We rephrase that in a community. Let's see. Green's improvement can still be viewed from token. It's not like that. So even Green basically analyzed this communication protocol and made it better. I'm not sure whether he made it better while he was still working in communication or from the perspective. But he eventually wrote this paper. I mean, by paper, I mean it's a 1.5 page thing he uploaded, right? Communication complexity, gateways. So what is communication complexity? So you have 8 people. Each one has an input with them. So they have some element of some set. They could all be the same set, right? Great. It's very important. So what they want to do is, for the sake of this talk, there's some function f which takes some possible inputs. The inputs are always coming from the set. So one input to each player, and the function outputs either 0 or 1 on the inputs. And what the players want to do is they want to actually compute this function. So player 1 sees x1, doesn't see any of the other inputs. Player 2 sees x2, but none of the other inputs, and so on. This is called the number in hand communication complexity, where you have your input in your hand, you can't see other people's hands. And the way they have to do this is via a communication protocol. So what is a communication protocol? So protocol basically specifies how the communication is going to proceed. So at every step based on previous communication, you specify which player speaks next. The protocol decides which player speaks next. And it also decides what they are going to speak based on the input that they have. So basically, it gives them a, say, PI speak next. What they say, and then the function. Either this or what the output.
This broadcast.
Yes. So when they say, when a player says something, all the other players get to know what was said. Okay, so we'll see an example of what this looks like. So we'll be considering the transcript of the protocol. The transcript is basically a detail of what all conversations happen in the protocol. So initially, when we start running a protocol, there is no previous communication. So the protocol just deterministically chooses which player speaks next. So let's say it chooses player I should speak, and it specifies a function which they should use to decide what they're going to say. So it decides PI and F. And based on this, player I is going to basically output. They're going to say M of Xi. So now the transcript has this one bit in it. Based on this bit, again, the protocol is going to decide who speaks next, and what function they use to decide, and then that player will speak next. And based on the transcript till now, which is these 2 bits, we can continue this. And it will continue in this way until at some point, based on the previous communication, the protocol automatically decides what the output of the protocol is. So this is the way a protocol functions, and the fact that it has to function in such a systematic way is going to be very useful to us. So one thing we can note is that when I'm specifying what the transcript of a protocol is, I don't actually need to say who spoke what, right? Because at the very beginning, everyone can figure out who's going to speak next. That's deterministically decided by the transcript. So we all know that if I say the transcript started with 0, we all know that player I was the person who said 0. And now that I've said that the first bit was 0, we all know who's going to speak next as well. So I don't need to specify who's going to speak next. I just need to say what they said. If I just tell you what bits were communicated, you actually know exactly which player spoke each of these. And so the transcript is just the sequence of bits. Now, on every single input, the protocol is going to end up outputting something. So what we want to know is we want to take all protocols that compute F, and we want to find out which protocol actually has the least cost. That is, the cost of a protocol is basically the longest transcript that can happen before it outputs something. And the number of bits here is logs. So the communication complexity of F basically is. You look at all protocols, by computing F, I mean on every single input, they output F of that input. And among all such protocols, we're looking for the cheapest one. All right. Now, based on this description here, we can notice that one very neat statement can be made. Suppose the input to the players was x1 to xk, and the transcript that was outputted was some string t. And suppose that on some other input, x1 prime, x2 prime, xk prime, also the transcript that happened is t. Then you can actually mix up these inputs in whatever way you want. So you can take, for the first person's input, I can choose x1 or x1 prime, it doesn't matter. Second person's input is x2, we say, and the last person's input is xk. And there's. Then this will also have the exact same transcript. This is called it comes under various names, but some people call it the cut-and-paste time. So basically, what's happening here is that no matter what your input is, the first person speaking is the same. We all know that what they said when in the case where their input was x1, or where in the case where their input was x1 prime, we all know that they said the same thing. So therefore, in this transcript also, the first bit is going to be the same. And now we can just use induction. The first bit decides who's speaking next and what function they're using, whether it was x2 or x2 prime, depending on who was speaking, whether it was xi or xi prime, it was the same output. Therefore, in this case, also it will be the same bit that is communicated. So this property is going to be very useful in connecting communication complexity and such problems. So let's consider a communication task. We'll stick to the 3 arithmetic progression for now. So we're defining a function f, which takes in an input x1, x2, and x3. And it's promised that these form, either they form a PAB or they're all equal to each other. So this is the promise. The input, either the input is of the form a plus b, a plus 2e. And what the function has to output, basically it outputs 0, if D is equal to 0. Output is 1, D is not equal to 0. So it outputs 1 if they're true 3 arithmetic progression, and it outputs 0 if they're all actually the same number.
I see. Oh, this is the function that now you're gonna try and compute.
Yes, we're going to try to compute this in the 3-layer setting, or in, I just didn't want to write k things, so. In general, we can assume that it's capable with the promised
So you
k.
get, I see, so you promise that the input is either an arithmetic progression or a degenerate arithmetic progression,
Yes.
right? And now you want to tell which.
Yes.
Ah. And now somehow upper bounds on this, you're going to relate them with this RK number.
Yes.
Does it go the other way, with lower bounds on
So
this?
it's the equivalent.
Oh, wow.
And
Now,
we're going to basically be just using this for one direction. Okay, so first of all, if let's stick here. So suppose R3 of n was equal to say C. Well, it's not really R3 of n. It's a color invariant. So it's not related to R3 at once, it's really the same. So this is a new notation I'm just introducing. This is asking how many colors do I need to color 1 to n, so that every color is free of creates.
also, this is more the London garden.
This is more, yeah, the longer word.
Oh, because somehow partitions of the tensor into cubes or whatever.
We'll see.
Yeah.
Okay. So let's where else is. Let's say that the number of colors needed to color 1 to n, avoiding clear arithmetic progression is C. This implies that the communication complexity of this function, which I'll actually give it a name, I'll say 3AP communication complexity together it's a function. So the communication complexity, communication complexity of is at most log of C.
The log, I mean, the ceiling is outside the log.
Oh, sorry. And the idea is, it's a quite straightforward protocol. So player 1 gets some input x1 from 1 to n.
So can you put the inequality on the call so that I understand? So
Okay. That's not.
right, so that means that that if I have C colors, I can partition n into C sets, all of which avoid 3 arithmetic progression. Okay. If I have at least C colors, then I know that it's okay. All right. Okay. Now you're going to give me a communication protocol for that problem.
Yes. Also, all these inputs come from n. So the protocol is quite simple. Player 1 is going to look at their input, which is x1, and they're going to say, according to this coloring, which we know exists, what color was x1 colored? Player 1 basically says color of x1. Now, if x1 was equal to x2 is equal to x3, then everybody agrees on the color of their input. Color of x1 is equal to color of x2 is equal to color of x3. And if they form a 3AP, then it's impossible for all their 3 colors to be the same, because this coloring avoids 3APs. Every color avoids 3APs. So That's basically it. All the colors of these are the same, if and only if these are equal to each other because of this promise. Like it's easy to find x1, x2, x3 that are not the same, but that all have the same color, but then they wouldn't satisfy this promise. In this promise, either they're all the same or they are the 3AB. Let's say 1. So the cost of this is log 3 bits to say the color of x1, and then 2 more bits to see if the other two agree on the colors. If they both agree, then they were all the same input. If one of them disagrees, then they're actually a 3A. This is one direction. Now, in the other direction,
Forward with the transfer.
so I want to say now that if the communication complexity of DAP PC is less than equal to C, then covering number is why is this true? So what we're going to do is for every single input from 1 to n, let's map x and n. Let's map it to the transcript that the protocol produces on the input x, x, x. Now we know the communication complexity is at most C. That means that there are at most 2 to the C possible transcripts that could have been produced by the protocol. So that means each input x is being mapped to one of 2 to the C values, and those are going to be our colors. It's obviously, if all of them got the same, so let's suppose that there is a 3AB, a genuine 3AB, which all got the same transcript. So that means x, x, x have transcript T, y, y, y have transcript T, and z, z have transcript T, and x, y, z actually form an 3AB. Now we use this property that says these two have the same transcript, so I can just switch them around as I want. So in particular, x, y, x also have the same transcript. Now x, y, x and z, z, z have the same transcript. So therefore, x, y, z also have the same transcript. But the output of the protocol is totally dependent on the transcript. So on these cases, it should have outputted 0 because they're all the same input. So on all these, if T outputs 0, that means T is also outputting 0 over here. So that's contradiction, which means that the protocol wasn't working correctly. And so we have that if x, y, and z are a VAP, then at least one of them has to have a different transcript than the others. So then this map is actually a valid color. You cannot have 3 numbers that are in an AP that all got mapped to the same color. This connection between such problems and the communication complexity is known by various groups, but no one knows who actually came up with it first. Like it's kind of folklore, but it's not really mentioned anywhere. So maybe I'll put together for this.
Okay, wow, cool. It's funny because that also means that any protocol for solving that thing can be made like one directional protocol.
Yeah, just one person speaks.
Or just one
And
person.
then the other people just repeat that also.
Yeah. That's strange. I mean, that's not true for me.
Right.
I mean, that's very rare, that function. It's like, um,
Also, there was nothing special about arithmetic progression there. This is just like any structure, the exact same for this for a product.
Right, but this, as long as it's this, you have some basis and you do,
No, it's not even like scale and translation invariant. Like I can give you a specific subset of n to the k where there are k pairs, and I want to say make sure that either all your inputs are equal, in which case you output 0, or your input is one of these, in which case you output 1. And like, it's in that kind of generality. Do we do protocols? So yeah, so that's okay. So now we have this connection between communication and combinatorics. So what Lineal and Feldman did was they said, you know, this. So there's one thing that I'm not mentioning now. We can look at it later. The coloring. So this is like a set size variant of the question. And here we're looking at a coloring variant of the question, which if you're just caring about sub-constant or not, they're not comparable. But when you have a bound like this, so you can show that this if and only if coloring is less than equal to 2. And so whatever this density is over here, 1 divided by that, plus like log n is enough colors. So this result of wherein already implies that only these many colors are needed, which in turn implies that there is a communication protocol of cost, whatever is in the exponent. So whenever you see this kind of a statement written anywhere, whatever in the is in the exponent here is what you should be thinking of as communication cost.
but also all these, all the lower bounds in this are, sorry, upper bounds. No.
Right, it's complicated to talk about number ones. Like if it's R, we're saying it's greater than equal to, but the number of colors is less than equal to.
Right. So lower bound on the number of colors will be a lower bound that you need will be a lower bound on protocol from communication. But then there's some translation, right? So these results saying that if you have enough density, let's see. So they say that if you have enough density, so those are upper bounds on R, right? These results that say if you have enough density, then there is an arithmetic progression.
Yes.
These are actually lower bounds on the communication protocol.
Yes.
Wow, that's a trick.
It's very weird. Like those lower bounds are extremely mathematical, and it's not easy to see them as lower bounds. But one of the problems with that is actually the statement that we just saw, that any such problem can be seen as one player speaking and then the other player responding. So that automatically makes it a slightly lower bound in some sense. If
Okay. So you want to say that the first player needs to do a lot of messages?
like there's no structure of the protocol that you can be using in your communication protocol, because we know that the optimal protocol does not have a structure. It's just one person speaking. So then it's kind of saying that any lower bound for this kind of a communication problem completely becomes this mathematical combinatorial lower bound, like in one set.
For the lineal trigon one is for corners, right? So they showed that the coloring version for corners.
Exactly. So they show that you can color n square, and such as you only need these many colors. All right, so I'll present.
The protocol.
No,
So you're gonna present the protocol.
no, not the, I can show a protocol corresponding to wherein, but I think it's better to introduce one more thing before the breaks. Okay, so I'm going to erase all of this pretty much. It's fine. Now we're going to go into number of. So the communication setting is pretty much the same, except that now player one can see everybody else's inputs, except for x1, and their input. Player two can see all the inputs except for x2, and so on. And we're going to be interested in the number on for communication complexity of a very specific function, which is exactly n. So this basically on the inputs x1 to x3 maps it to 1 with the information and 0. So this was introduced by Chandra first and Lipton. Both the communication model and that content. This is what started number on for communication complexity, is the relation of that exact end problem to corners. You'll see. Let's just analyze what happened with the clips. So inputs, globally speaking, are x1, x2, let's say. And let's use n prime to denote the summation of the second. What does player one see? Player one does not see their own input. They see x2, x3, and all of let's say. Player two sees x1, does not see their own input. X3. On player k sees x1, x2, x1, does not see their own. So you can think of it actually as a number in hand problem, where the inputs are actually given to them like this, under the promise that all these x1s are equal, all these x2s are equal, and so on. And it's the same. Number on port is number in hand, but with this promise. And yeah, so the task they want to do now is they want to find out if I, find out what's missing in my input. Would that sum be equal to n or not? Now, I'm going to rephrase this problem a little bit. So what I'm going to ask all the players to do is assume that the sum is equal to n. So what I mean by this isn't, just output yes, they're equal, but just fill in their inputs under the assumption that the sum is equal to n.
They want to know if they're all equal. Okay. Right. They want to know if all their
Right, exactly. Yeah. So what is this person going to fill in as P1? It's going to be n minus the summation. Okay. And I can write that as x1 plus n is what it is, and n prime is what it is. So they will actually assume here that they have n minus this summation. I'm just rewriting that as this. Because now if I add up all of these, that's summation xi minus n prime plus n, which is equal to n. Player two also fills in something very similar.
What is the difference between n and the prime?
So n prime is the actual sum of all their inputs. We don't know, it's just, we don't know whether the sum is equal to n or not.
Also input, yeah.
Sorry?
And prime is also.
No, n prime is not an input, no. And n prime is just something I'm defining so that we can think of it as well. So there is a fixed n in the definition of exactly n. And what they want to output is, yeah, so basically what they want to output is summation xi equal to n. But actually summation xi, as an outside observer, we know that it is n prime. And now if I ask all of them to assume that their sum is equal to n, then each pair is automatically going to assume that their input is x1 plus n minus n prime. If the sum is actually equal to n, then they're assuming correctly. If the sum is not equal to n, then they're assuming wrongly. Okay. So this task is not easier or harder than exactly n. If they want, they can just refuse to assume it. They're left with exactly n. And they didn't need any extra information in order to fill this in. Just by looking at the others, they could fill it by themselves. So I've not given them any power. I've not taken away any power by asking them to write their inputs in this format. Now I ask them to forget the last column. So that basically means they're going to ignore this part of their input. Now, I'm not giving them any extra information by asking them to forget the last column. And I'm also not taking away any information because they can reconstruct the last column because they're assuming that this sum is n. So if they want to get back what the value of xk was, it's n minus the summation. If everyone does n minus the summation, they will get back exactly what they were asked to forget. Okay, so now this is a different form of the exact same question exactly, where pair one's input looks like this, pair two's input looks like this, and pair k's input looks like this. What they want to know is whether all their x1s are the same and all their x3s are the same. Okay. If n is equal to n prime, everyone has gotten the exact same input as they see it. These k minus 1 inputs are exactly the same for all of them. If n is not equal to n prime, then there's this one vector here. This one vector is the same vector plus n minus n prime times e1. This is the same vector plus n minus n prime times e2. And so on n minus n until this person will have n minus n prime. Ek minus 1. So what they have after doing these two operations is they actually have a corner. If the sum was equal to n, then it's a trivial corner. If d is equal to 0 and it's not equal to n prime, then it's not. Okay. So basically, the number on forehead complexity of exactly n is the numbering and complexity of this problem, which, as we already know, is exactly the coloring number of the first problem. Now, from this version of the problem,
This is that for corners this holds the equivalence between combinatoric problem and that holds for an arbitrary structure rather
Yes.
than this also holds for
no, this is quite, well, I don't see a more general way to do it. There's probably some kind of linear transform interpretation of it, but I don't think it's completely done.
Everyone except for TK can recover X.
Everyone except for
TK can recover XK. The PK didn't actually start with XK, so that's
they're recovering whatever they have.
right.
Everyone can recover whatever they have, but it's not necessarily a state. Um,
All you have to do is show a 2 to the whatever, like sort of log in upper bound, and then I'm going for a communication problem.
just the data, so just upper one.
Right. Okay, upper.
Um, we could make number on it. So we have this number in hand problem, that is the corner problem. And
Okay, so now you want, so do I get correctly, you want an algorithm that communication protocol that runs in the root of little n bits. Whatever, little n would be the number of bits. Root of little n bits, and you're interested in improving the constant before the root of little n.
exactly. And we're interested in putting root of little n too, but all we can do is improve the constant.
Oh, sure, okay, yeah, sure, okay. Wait, oh, I see, but then a lower bound of root little n. That's interesting, okay, but, okay. It's for the special protocol where.
So wait, now, so you've taken us to the number on the fourth model, but then we've now gone right back to number.
That was to see the connection to the numbers.
Sure. So instead you're proving on upper bound. Okay, so you're saying to prove an upper bound on the number in hand protocol for corners, which gives us this is enough to prove an upper bound on the number on the forehead of exactly F.
Is exactly the same. as
Yeah, perfect.
proving it.
Okay.
Before that, let's do one more thing where every player here takes their input that they see here and does like summation I times we really haven't progressed. So now, so I'm now defining a linear transformation. Which so here's a way to transform k numbers into one number. And suppose each of these players does this by themselves using these k-1 numbers. Then, what player one gets is summation xi plus n minus n prime. Player two gets is summation xi plus twice of n minus n prime. And it goes on this way. Player three will get 3 times n minus n prime, except for like player k, who just gets summation xi. Oh, sorry, not summation. Summation I xi. So in this case, player one has come up with a number, player two has come up with a number, player k has come up with a number. Player one doesn't know what number player two has come up with, because like that would be equivalent to knowing n minus n prime. But this is a zero cost protocol, no one has spoken anything, and each of these players have come up with a number such that these numbers are in an arithmetic progression. So this is basically the same idea as if you can do corners, you can do everything, just instantiated with arithmetic progressions in the communication complexity set. So if you have these numbers, if these inputs which are corners, you can transform it into these inputs which are an arithmetic progression. And the difference in the arithmetic progression is zero, that it's a trivial arithmetic progression, if and only if it's a trivial corner. So solving this arithmetic progression question definitely helps with the answer to the corners question, but the other way around might not work.
So now you just proven the reduction that you said,
Yes.
lower bound on R.
Yeah, well, that's basically so in the coloring version is much better. Coloring k minus 1 corner time is less than equal to coloring k version. Character. That's basically this. Well, technically it's kn, but these terms have at any prefix.
Oh,
I should not actually be saying n, but
okay. Yeah.
right. We have number on coordinate exactly n, k players, which is equal to number in hand, so let's say it reduces to number in hand. And solve this thing, so it's and there's a zero cost in the relation.
Are we gonna use that for the proof or
We are.
you are?
Right,
Wait, but we were going to show an upper bound.
right, so I'm going to show an upper bound for k, which will imply an upper bound for exact.
Oh,
And I'm not actually for k, if I do that, I'm actually improving better.
it's again called.
If I improve the k version, I'm actually improving this one, which we don't know how to do.
Okay.
So it won't exactly be through this, but we'll see.
So once again, we're back in the number.
Once again, yeah. So most of the protocol actually happens in the number. But we're going to be using one trick eventually one number on coordinate. Okay. So what I will present, so the plan for the rest of the talk is find out how this protocol works. Okay. So that protocol is basically a protocol for this problem. We're going to see a sequence of reductions. And it'll finally be able to output an answer. All the reductions are very similar, so I'm just going to present one of them to be clear that it works for the others. And then after that, when we figure out that that's how the communication protocol looks, we will actually jump from here to here, where the cost here, if it's C1, C2, the cost of C1 will be less. So if you look at Rankin's protocol, it looks like this. Its first step, we will bypass with a lower cost by using the fact that we were on the number on coordinate number. That's very normal. Right. I don't know if people want to break or something, but this is a bit.
Yeah, let's see that.
Alright. So we already saw this variant proof that there is a large 3A set. There was two steps. In the first step, we just took those integers to equate to representation as of these small entries that must be by 2. And in the second step, we refine that further based on what the length of the vectors. So we started with n, and then we took a subset S with small entries. And then we split this up again into Fn. Then squared. And since these are small entries, then the vectors here, if they were in a 3 arithmetic progression, and we know they can't be in a 3 arithmetic progression. And because we're only dealing with small entries, their corresponding integers also could not have been 3 arithmetic progression. We'll do the same thing now in communication. So this is the protocol for non-wherein 3 So I'll just state what the protocol is, and you will see soon enough why it is. So here we only have 3 pairs. So say the inputs are x1, x2, and x3. Okay. So in the first step, what I will ask everyone to do is to compute the base Q representation, where Q and D are set appropriately. We already know how to optimize Q and D. So we compute the vector versions x1, x2, and x3, which are in Q2D. Now we compute basically the largeness of each vector. So what we compute is again vector with s1, s2, and s3, 0, 1, 2, where s1I is equal to 0. One I is equal to 1. So if you think of so let's look at Q to the D. Let's actually draw a grid. Then Q,
So somehow this will give me more, this will give me a partition, right? So
yes.
I guess that's why it's more complicated than the other things.
I think once you see what this is doing, it doesn't really look more complicated.
Yeah, you're partitioning 2 to the D into 2 to the part, 2 to the D parts, and it is in specifying which part it belongs to.
That is correct. And specifying what part you belong to is useful for one more reason, which is useful. So let's say you're trying to represent your vector here, x1. X1. It has d entries, each one from 1 to q. So you can think of it as for each coordinate, you're just specifying which entry it is. So all what Alice is, what player 1 will compute, the S1, is basically 1, 0, 0, 1, 1, 0, 0. Saying those are my coordinates in order.
Well, 1, 1, 1, 0, right?
Yes. This is 1 because it's in the upper half, 0, 0 because they're in the lower half.
Yes.
1, 1, oh, exactly. Okay.
Yeah.
So why are they doing this? The idea is if 2 people compute different vectors here, then we already know that the inputs are not the same. Okay.
So by sending F, we now know, always,
And one more thing happens. Is x1 minus. So basically what we're going to do now is whatever this vector is, I'm going to take whichever entries are large, and I'm going to put them in the same position, but in the lower half. Basically, this one's done here. And what operation do I need to do to my inputs in order to say? So initially, what we had was the representation of x1. And then after moving it, we have moved to the representation of the different integer x1 prime. And what is x1 prime? It's just the same as x1, except each time there was a 1, you've subtracted q by 2. Here you've subtracted q by 2 times q cubed, q by 2 times q to the 4, q by 2 times q to the 5. That's all we've done. This whole thing, let's accomplish it. All right. So all of this. So now the vectors corresponding to these all have small elements. And say layer 1, we basically now say and we'll say the length of we start off with just 3 arbitrary entries in 1 to n. We looked at them as vectors. We figured out what value should we shift them by in order for all of these vectors to have small entries. And that shift value is completely decided by the string s1 or s2 or s3. Yes. And we know that x1, x2, and x3 are in an AP, implies that x1 prime, x2 prime, x3 prime are in an AP if all of these vectors are the same, because then they're all being subtracted just by the same number each time. And yeah, that's the protocol that follows from there. What's the cost of this protocol? It's d bits here plus log of q squared d, because this value then was q squared d. And if you remember our calculations, we had exactly the same kind of calculations for the density. And n to the minus 2 to the minus d means log of. This is exactly the same indication. So in fact, by moving the coloring, by translating this variant thing, we've not lost anything. All right. But what we're going to do is we're going to split this, even though it's just 3 steps, we're going to split this into 2 protocols to make it more modular. So we're going to look at this protocol. So what does this protocol do? It takes as input three numbers, which are promised to be in an AP, possibly a degenerate AP. And what you've come up here, first of all, say the P1 says that. Just remove this one. So what they've managed to do is they've managed to find out three vectors which are actually in an AP. You started with three numbers that are in an AP, and you found out three vectors that are in an AP. And these vectors are all the same if and only if these three vectors are all, if these three numbers are all the same. So what really happened here was we had a number in hand, and we reduced it with the cost of b. We reduced it to number in hand, the vectors. So what do you need for this reduction? The output of this reduction must satisfy the promise, and they should be equal if and only if these numbers are equal, both of which are equal to it. All right. In the next step, what happens? Reduction is going to be, if I can solve, if I want to solve creatively, I've communicated the bits, now all I have to do is solve creatively. Right?
Now split these vectors by the norm.
Right. Now we split these vectors by norm, but there's something actually deeper going on that actually Rankin realized. It's not just the norm of the vectors that was being calculated. I mean, it is the norm of the vectors, but the norm of the vectors had some special property, which is if you have three vectors in an AP, then by computing the norms, what you've done is you've reduced the problem to it's a quadratic progression. So there's the same. If V1, V2, and V3 are three vectors in an AP, then the norm squared is actually becoming a quadratic progression. What does this mean? It just means that there is a quadratic polynomial such that this is P of 1, P of 2, P of 3. Now, the problem with this statement is this is actually a trivial statement. Every three numbers are in a quadratic AP, because the quadratic polynomial can be made to take three consecutive values, no matter what the values are. So this really isn't saying much. But it would have said much if we had extra vectors. We had V4, which were in a vector arithmetic progression. We did V4 squared. Then this would actually be. This is no longer a trivial statement. And not only is it just for some quadratic polynomial, so by quadratic polynomial, it could also have degree 1 or degree 0. Those are all technically quadratic polynomials. But this is a constant polynomial if and only if all these vectors were the same. So why is this? What does it mean for vectors to be in a vector AP? It means that in each dimension, the entries of the vectors are in an AP. These are three vectors, or four vectors, and I say they're in a vector AP. It means that these four entries are actually in the arithmetic progression, and these four entries are also in the arithmetic progression, and so on. Each of these is basically an arithmetic progression.
Wait, we have something stronger, right? The jump is the same. I mean, being in an arithmetic progression as a vector is not the same as each of its entries being, because it could be a different D for.
Right, but it could be a complete breach, because in the vector, if this is just B2, we think this is B1 plus W for every different entities.
Oh, I see. Oh, yeah. Okay. Right. Mhm.
So in fact, I want to say vector AP is just the same as and of independent A's. Actually, let me go clear. And the vectors are the same if and only if each of these APs are trivial. All of the APs have to be trivial in order for the vectors to be trivial. Now, what happens when we take P1 squared? So that means that there is a linear polynomial here. So let's call them actually P1, P2, so P2. This is P1 of 1, P1 of 2, P1 of 3, P1 of 4, P2 of 1, P2 of 2, P2 of 4 for some linear polynomials. And what B1 squared is computing is basically summation Pi of 1 squared. That is exactly 1. And summation Pi of x squared is, if you just expand it by expanding out each of the Pi of x, you have linear terms here that you're squaring and then adding up. So then that is a quadratic polynomial in x. Find q of x. Then degree of q is equal to twice maximum degree of x. And in fact, this is equal to, there cannot be a cancellation of the largest monomial square. The largest monomial square has a positive coefficient, so summing up them up will not cancel it. The degree of q is truly twice the maximum degree. And then we define q like this, this is exactly q of 1, this is q of 2.
So what is beyond?
So I'm claiming that these vectors form a vector AP, which means that each coordinate of them forms an arithmetic progression. And what does it mean for something to form an arithmetic progression? It means that there's a linear polynomial, which I'm calling P1 for the first coordinate. Just that it's P1 of 1, P1 of 2, P1 of 3, P1 of 4. So this gives us a quadratic polynomial, and we want to continue this down this chain of reactions. So now that's essentially all of ranking is basically this. You might reduce it with some cost to NIH. So suppose I started with k numbers in arithmetic progression. I do the same exact trick and I end up with k numbers in a vector arithmetic progression. Also, let's call arithmetic progression a polynomial of degree 1. In the next reduction, gives us numbers that are in a quadratic progression. And then after that, so we know how to do this step. We've seen that picture. We know how to do this step. And also this step has cost 0 as usual.
So for this to make sense, you do need k to be bigger than 4. But
For
at
this
least
step,
4.
we
At
need
least
k
4.
to be. Yes. the vectors that are in quadratic progression. Then you want to continue this as long as it makes sense. What is happening? Okay, so first of all, we saw this part, how you reduce it to vectors that are in an arithmetic progression just by making sure that they all have small values. So at this point, all the players have a vector in their hands, and all they're doing is they're finding their length of the vector square, which is a cost zero communication protocol. You just have what your input is and you're taking its length squared. So with cost zero, you've doubled the degree, and you've got these units. So what is this problem? This problem is you're promised that your inputs actually are Q1, Q2, Q3, and so on. And you just want to know, are they all the same? What is this problem? This problem is exactly akin to the vector A. It's basically a vector. Each dimension of it is a quadratic progression. Vectors. Each of those lines is actually a quadratic progression.
So once that we can continue for cost log k times d, we can get it so that the degree is at least k2.
That is exactly right. Yeah. So, that's n. So what is the cost here? Cost of d. Now when we do the second step, the cost is actually going to be smaller. It's going to be cost 2d. Cost 4d. So this is going to require us to actually be a bit more careful and set different dimensions each time when we're writing our number as a vector. We'll be doing this in such a way that d1 can be large, but d2 should not be large because it's being amplified. d3 should not be large, and so on. So yeah, this is the layout of it. So why is the cost increasing first of all here? We've seen this, we've seen this. And in fact, every time there's a reduction, all of these reductions are the same reduction. You're just taking their length squared. So we've actually seen all of these reductions.
So the Q also changes at each step.
The Q also changes.
So the Q is such that it has to be enough to represent
Yeah, so
the number.
right. So you want basically the Q2 to the D2 should be at least Q1 squared D1. Because that's the size of the number that represents them. Over here you have numbers from 1 to n, then we have vectors in Q to the D, then you have numbers from 1 to Q squared D.
Oh, okay.
So that's where so this is actually a tougher problem. Like this is a superset of this problem. If your numbers are promised to be an arithmetic progression, then they're also a quadratic progression.
Right.
So this is a tougher problem, but the input size is so much smaller that it makes sense to do this and solve this.
Okay.
Each time the input size is reduces.
By a lot.
Right. So once you set the Q and B, you want each of these problems to be equally hard so that everything balances out. So you'll set them in some way so that they're all. Okay. You know, that part of the presentation is messy. I think we've written it fairly well in paper, but I don't think it's nice for recreating on the board. Question on there, like our this working. And the family is big things. Okay. X1, X2, 1. There are two vectors. In the QB. If they form a degree M progression,
But just to understand now, the first time, well, the n is not much smaller. Did I get that correctly?
the what is coming?
Once you go to the second round, the capital
Yeah, the capital N is smaller.
will be much smaller, will be like shrunk logarithmic at each time.
Yes.
Okay, good. Okay. Now you're saying.
But it's not logarithmically because it's like square root logarithm.
Oh, also,
Seven.
okay, also you can only do this like a few times, right? Because soon enough, the degree will become larger than k.
Until it's K, at least K over two.
Yes.
This, the best you can guarantee.
Right, okay.
Yeah, like log K.
Can you finesse, I mean, not that you would want to, can you finesse it so that's K minus one? Like, could you then start doing degree only, like. Once you reach a high degree, start blowing it up in smaller increments instead of doubling?
That is a question which we are very interested in.
Oh,
We
okay,
don't know how to do anything apart from this stuff.
okay, would it be useful to do so? If
It would be
next one.
insightful, at least there's a new idea there, for sure. And yeah, we would want to see that. Like this log K is actually sitting on log K, so. In fact, if you have a 3 AP or a 4 AP, you have the same density bonds. But then when you go to a 5 AP, suddenly we get much better performance. Because you can do two steps. With the 3 AP or 4 AP, you can only do one step.
So this would help with the 6 and 7.
Yeah, it will help in all the things.
Isn't that the opposite? Doesn't that mean like for 5, it's way better than normally it would be? Like, whereas for 8, it's what you'd expect. Wouldn't it be worse if it was the floor? Or well,
So you can make it floor of log of K minus 1. They're the same statement. Oh, sorry, log of floor of log of 2.
like, if you, my question is, if you got rid of those ceilings, would it be better or worse? Oh, I guess it's worse. Or sorry, it'd be better if you got rid of the ceilings.
No, which should be worse if you get rid of it.
So if you get rid of the ceilings, then the log K shrinks, which means that every grows.
Oh, there.
Because you're taking log into. No, you're taking log into a bigger root.
This is good.
Yeah.
For 3, we have square root log n. For 4, we also have square root log n.
That's what
5, we have 2. So it's better in, yeah, so there's a way to think of it.
Yeah.
Is this the true square root log n or is this the true square root log n? It's the question.
Yeah, my point is just that when you bump up that 2 to a 3, that means that the whole value gets smaller, which means that the negative gets smaller, which means the density.
Think of it as a communication protocol. So this is more efficient.
Right, that's more efficient, which means you get better with lower bounds.
Better upper bound.
Better row bonds on this.
Better lower bounds on arithmetic. Right, and that's what we want. So actually, the ceiling is good.
So ceiling is good.
Yeah.
Right, yeah, so exactly. So removing the ceiling is bad.
Right, so back to my original question. You put the ceiling there, if you got it more fine tuned, like you could do it for the same cost, you could get to exactly K minus 1. What would that do? Because I thought you were saying you would remove the ceilings, but that's not what we want.
No.
Yeah, it does something else.
It would probably be like maybe log of 2K but without the ceilings or something like that.
Oh, okay.
Or 2K minus 1 without the ceilings. I don't know what it would be.
Okay,
That seems like a reasonable way to interpret between the two.
okay, good.
x1 to say x and plus 2 is a sequence of values of an MGP polynomial. And their vector forms u to the v are such that they have entries less than equal or less than by 2 to the n. Then so this is a generalization of what is happening in the arithmetic progression. We said if you have an arithmetic progression and when you write a base Q representation, all of them are smaller than half of Q, then the vectors are also in an arithmetic progression. No carries will happen. And you can generalize that statement to higher degree polynomials. If you have a degree m polynomial, and you guarantee that each entry is sufficiently small, then you can still guarantee that no carries are going to happen, regardless of what the polynomial is.
So the deal is that we have to send like n times d bits.
Exactly.
To say which like
Which we can have, what I have to shift by to get to the smallest beginning each.
Yeah.
Assuming this protocol would be very straightforward. You just find out what shift it is. Requires m for each dimension. So with m and d bits, you communicated what shift it is. And then your vector actually form a vector polynomial progression of the same degree. That I haven't proven it, so it's not obvious why it has to be the same degree, but the proof shows that.
Wait, so I'm missing some, I'm missing something. Oh, I see, 2n. Oh, the n is a degree. Okay, good. So the degree was 2, hence you get 2, because that's, you have to send n bits.
You continue this as long as the degree is like at most k by 2. And then at some point you're left with a number in hand question that you cannot improve. You're left with some from which you don't have a reduction. At this point, Alice or player one just said what their input is, and everyone else checks if their input is the same. So that was what was happening there. Everyone was checking their vector length, and then one player would just announce their vector length, and everyone sees if it's the same. That part is still the same. And it makes sense because throughout this whole thing, we're ensuring that if your inputs at the beginning are the same, I mean, your inputs at the beginning are the same, if and only if they're the same here, if and only if they're the same here, and so on. So at the end, you really only need to check as well.
Okay, so you're saying that for the parent version where it's 3, there was no reductions to, you wouldn't blow up the degree at all. 3 was already the best that you got, but even just doing this one translation to the right one time was good enough to get the square root. And then Rankin says if you can iterate this in this fashion, you pay something a little lower wherever, but you end up with like the log k degree.
So you, in order, at the end, you try to balance everything, and then you try to make each one of these cost be log k root of log n.
Okay, I still have a question, right? Because it was very obvious that like a line only crosses its direct two points.
Right. Yeah, but now
once you get to the end, it's not a line anymore, it's like a degree something surface.
Right, but we're not actually using that anymore.
Oh.
So, so what was the addition there? You went from here to a quadratic.
Or you're saying if they're all equal, they will still be equal, and if they're different,
It would be-
they will still be different. People will be one.
That's, yeah. Yeah, so this is pretty equal. So the statement there, I think if you want to see it in a generalized form, it's really saying that a quadratic polynomial only has at most two roots. So if your vector length, which is a polynomial in the player number, actually was the same at 3 points. Yeah, so a quadratic polynomial can be the same at most 2 points. If it's the same at 3 points, it's constant. And that's the same thing that's happening here, except with a larger degree. And this proof is really nice, but I don't think I should do it now because it's already been long enough. I will just skip to what we did here. But at some point, read the paper.
But the reason this and thing that's because this degree to norm, the usual norm is a degree to column.
Yeah.
And think of higher norms and then say, then you look at sets that points that which equal a particular value according to R, and then look at that.
You know the, are you not?
So if you just apply this, what are you done?
If I apply this,
Then you get
so all we've done right now is recreate it, right, in a communication setting. Right.
Oh, so this gives it to you for progressions. And you wanna do a performance, like
Yeah.
what do you?
That's it, we've got the progressions. Along with this reduction, which is that linear map from corners to any predictions. We now have it for corners as well, but we want something better. We haven't improved upon that yet.
Now, so this is just rank in the language of communication complexity.
Yes.
And so now there's something like this lineal Schreibman
Right.
must have also used some trick.
So linear and Schreibman. So I presented wherein in the language of communication complexity. Linear and Schreibman didn't
I
do
don't
that protocol. They came up with a different protocol which just had the same. Right? And with that protocol, we were able to make some improvements. I'm not sure. Yeah. Also, wherein as a communication protocol is also known, like it's there, for example. Textbook on communication complexity. They have the protocol version of this, but I don't know what it is. Or maybe it was easier with the idea that they have things. Yeah. So, if I can get to what we do. This is really what so no one had really written this down before, like looking at, oh, there are vector problems and there are integer problems that are separate and modular. But once we wrote it like this, it became clear that what we should really be trying to do is get a vector version of this and then reduce it there.
So this only saves you the D1 costs essentially, like it only saves you in the first round.
It saves you some cost and then you rebalance everything so that that's all the way to do it. But yeah, that's the problem. So as soon as you move here your number in half, you can no longer use number on forehead characteristics. So you can't, like, it would be wonderful to keep some number on forehead characteristics going after this question, but figure out how to do that. Right, and notice that vector exactly n is, it's exactly what you think it's. You have a bunch of vectors, you're asking as vector additions that exactly n, which means that each coordinate of this is an exactly n instance. So you can reduce each coordinate separately with the same reduction that was a cost zero reduction and end up with instances of arithmetic progression, independent ones, which is the same as vector. Vector. And that's clear, but
It's the same reduction on each vector point.
yeah, it's the same reduction on each coordinate of the vector as this one, which is done in parallel. Yeah, absolutely. Okay. Now we finally get to think of the number on the coordinate setting, which it's sometimes fun to think about. We have x1, x2, the next state on coordinates. And the question is, do they sum up to be equal to n? And we're going to rewrite that in some way. We're going to ask it as x1 plus x2 plus xk minus 1. Is this equal to n minus? Now what we're going to do is we're going to write these in their vector format. So we've got x1 plus x2 minus 1. Is this right? So the fact that equal to here. We've got this on one side. On the other side, we have n minus xk as a vector. So remember, player k can see all of these inputs. So even though this vector addition might not actually equal to, right, this need not be equal to x1 plus x2 as a vector. Player k knows exactly what the difference is between these two, because they can see the whole vector. So now player k has to communicate some vector, the carry vector. Okay. So if player k manages to communicate this carry vector, our reduction is done. Each player here, or rather, you can think of it as just only change x1 to say x1 minus bc. Let's actually state it in a bit. Let's say this is equal to this plus bc. So then every player is going to look at x1 and think of it as x1 plus bc. And then your inputs.
So since it's minus, okay.
If this is equal to this, minus bc squared. Minus. there.
I suppose the PC would appear on all fours, right?
No, just one. Right, so now what is the summation of all these vectors? It's
Oh, sure.
going to be
Sure, something else.
exactly equal to this minus that, which is 0 if and only if the sum of the vectors.
Didn't make sense.
No, because of the way we rewrote it.
Oh, fine, yeah.
Have you seen it's the carry, so it's like in some places, it's really you have to remove the carries. What is it? So if you sum in between, so if you sum them as vectors. You sum them as vectors. Okay, so what do you want to
So this is some of the vectors.
you want like if you implement this, you give it directly n minus xk. Yeah. Right.
For what we see, it's only a question of we don't care about elements. It's just a question of this stuff.
Right, so the carried vector is what? You have to go into each coordinate. And you have to figure out how much moves to the next one. In the number,
Yes.
but also you need to subtract what you kept there, right? That's the carried vector. I'm trying to just understand.
Yeah.
the carried vector,
But,
Right, so if you have like, 7 plus 8 or something.
yeah, actual numbers.
7 plus 8, replace 10 or 7.
63. Is it? Yeah.
So 7 plus 8 has a carry.
Right. So what you expect the sum is 5, 0, 4, but the vector sum is 15, 9, 3.
Right. So now I have to figure out, so you need to
So what
subtract
my carry vector is literally this.
minus
Okay, there's a carry of 1.
Oh.
6 plus 3 plus 1 is a carry of 1.
of a carry. Yes.
7 plus 2 plus 3. Six plus 2 plus 1 is a carry of.
Right, and now what do we see actually? We see it minus 10 on the left or something? Right,
Right, so we're trying to figure out
what we see it,
what the sum is. We have the vector sum,
okay,
we need to figure out the sum, is that sum?
yes, I think so.
So the vector sum, or is it sum is equal to?
Right,
The vector sum as an integer,
right, plus, and what's the vector now? It's 1, comma, minus 8. No,
Right, so
1,
I
9, 1, 9 minus 10, I guess.
I want to say time.
Oh, no, sorry, yeah, 1 minus, right? It's, so I'm trying to figure out what we see is, and I think in that case, it's 1, minus 1, minus 9, minus 10, right?
1 minus 9, yeah, if it's something very much like that. Yeah, so it's, yeah, exactly. So it's, basically you're adding q to the d minus q times q to the d minus one as vectors. Right, so you're really adding zero, which is fair because this vector sum, if you write it as a base q number, it's actually equal to 905. 50 plus 9 times 10 plus 8 times 100 will be equal to 905. But to make the sum and vector sum the same, I'm just going to be adding this into the carry vector's d format. So if the carry vector's d format is 1, then I'm adding q to the d. Yeah, I'm adding 1 comma minus q.
I see. I see, so actually only you have to give this binary vector, that's
You
all I
really have to just
understand,
give the vector.
and the rest we know, okay, yeah, makes sense, yeah, right. Okay, so that's, d bits, I guess,
Binary vector, if there are two players.
huh?
If there are two players, it's a binary vector.
Oh,
If you have k players, you're doing some of k things. There's carry can be as large as k minus 1.
right, so then it's a log k vector.
Right. So then you have a d times log k vector, which is a much worse reduction than this.
Okay.
You can make it a binary vector. I mean, if you think of it as a binary vector, or at least in the case of 2, the constant d, which is just equal to this. So it seems like we haven't yet gotten any savings, even by communicating we see.
Oh, I see. Oh, so now, is it just want to efficiently both carry vectors? Is that all that's at stake?
Yes, that's all that's probably efficiently employed.
Because you're saying, now you're gonna say that not every vector is a carry vector.
Not really. Every vector I think can be played. But there's another number on called trick one. Which is
And for upper bounds, number of word tricks seem like things you can just be able to write.
we want to know more because it's hard to come up with them, but once you have one, it's yeah, you really basically should use it.
Well, I see, so like, there's real hope that, but why don't you leave the number in format model?
What?
I mean, there's real hope that you maybe don't have to leave the number in format model,
No,
and you can improve the economics by a lot. Maybe.
Yeah. Exactly 1 sub 1, and this is linear, and go to exactly 2 n. Do that whole hierarchy, but just
what's taking I'm not right.
All right. Okay, the goal is still to encode this.
Yeah. So first of all, even though VC can have entries from so each of these is an entry of like 0 to k minus 1. You only have to convey these values modulo to each value modulo. Why is that? It's because as player 1, I already know the summation of all of these. I just don't know what my x1 is. Which means I just don't know if I have been added to push the carry to the next bit, or is the carry the bit that I'm already seeing. Like the number that I'm already seeing. So if I see a carry m in the,
So player K now will send a message that player 1 will understand.
then all the players will actually understand it. But it's true that
not all players, right? Because only x1 sees exactly x2 to xk.
right, but x2 sees x1 and all the others to xk x1.
Right, but for them, they don't know if it's going to push. Oh, I guess.
So yeah, but player K is not telling you whether it's pushed or not. Player K is just telling you what this number modulo 2 is.
And so all of them can calculate whether their own value pushes it over with respect to all the other values. Do they all need to know that, or just x1?
I think everyone except for x1 needs to know. Because this is the number on forehead.
Yeah, good.
Okay, I'm still there, so. So the carry, I agree, it's a number between 0 and k minus 1.
Yeah.
And you're saying that the last player will obviously know what all the carries are, just sends that number in mod 2.
Yeah, each coordinate mod 2.
Each coordinate mod 2. Oh. Oh. So you're saying that like, so you're saying that, no, yeah, so you start from the right now. And the
Yeah,
player
start from
that
the right.
doesn't know X1 can figure out the sum of all the others. And now he's gonna add his own thing, but he doesn't know what his own thing is. So he knows the carry, he just doesn't know whether himself. And adding this thing will push the carry to go one more or not.
That's all that is number, you can push it one more or not.
And if it pushes it one more, it will change the carry, and if it doesn't push it one more, it won't. So now you know this number, mod 2, so if you hit the right mod, then you know I'm not pushing it over, but if you hit the wrong mod, then you know I'm pushing it over. So now I learn the actual carry, which is a number between 0 and 10.
And once you know the carry, the same logic works for the second.
Thanks.
That's pretty.
So this would be a really good trick to be able to use in later rounds, right? We're paying 2D, 4D, et cetera.
It would be very.
Right, this is
we
going
don't
to be D the whole way.
I think I had thought so initially, but I don't know, it's been a while. I don't remember if I changed my feedback at one point. But
Wait, okay, so, and that's the equivalent, right?
no, that's, we're just really digging into this.
Oh, no, now we're in lead. Oh, I see. Okay,
So we've got, so I should mention, Linear and Triton did use an encoding argument, which carries are more likely and stuff like that, for a random input. Green used a very nice trick, once we figured out what it was, because he wrote it in combinatorics, I wasn't clear what the trick was in communication.
sorry, because you wanted what?
As a combinatorial statement, he just said, oh, that this is the set, and we're like, why is this the set? But then once you figure it out, it's a very interesting. So it's a combination of both of these that we use even now in a little bit more. And it's so first of all, what we're going to do, as Dream does, is we're not going to write our vector in the normal base Q notation. So instead, what we're going to do is we're going to write it in a notation that is like this. So in this base, this is still base Q, but it's like shifted so that every coordinate is between -q/2 and q/2. And the reason you want to do this is that if you sum up random numbers like this, the carry is going to go towards 0. Actually, I'll leave this for a bit later.
But what's your idea, that there's some set of numbers which are very easy, and then a small set of numbers which are not as easy, but then you just communicate with that or discuss it, or what?
So this is a number on fourth grade in this case, but we'll get to it. So let f be, let's actually. So that v1 till b k-1 be numbers in q to the d, vectors in q to the d. And our question is, what is their carry modulo 2? One second. So what is the corresponding? What is the distribution?
Okay, let me just prepare. So you're going to tell me how to efficiently communicate the carry mod 2.
Yes.
And now by all what it said, that's enough.
Okay. The distribution of the carry vector 1, 2 of summation. So it turns out that this distribution, so let's just see an example. Sorry. If you take two numbers, and so also we'll do another trick here of imagining this is actually R1 and R2 to R2 minus 1, uniformly picked from the interval 0, 1 as real numbers. And our question is summation Ri, does it belong to mod 2? It's belong to 0, 1. So in this case, we'd say that Ri mod 2 is
Well, I'd say it always belongs to 0 to 1.
is mod 2.
Oh, much less. Yeah. Right. Right.
Oh, you're thinking, wait, oh, you're thinking of these as real numbers or something?
Yeah.
Yeah. Mod 2.
Yeah, these are real numbers. So it's a
I see, yeah, sorry. Yeah, that's good.
I mean, that's really good. So the idea is that's what's happening in each format when I add these vectors and just making the queue continuous. So it's from 0, 1. And right, when is the carry? So every time I go past 1, I'm pushing the carry beyond q. And the carry mod 2 vector is changed its value and goes beyond to carry mod 2 value comes back to 0. Is that translation? Yeah. Okay, so this is the question. And
And the idea is that the 0, 1 model skew because Q is large.
yeah. So we actually do this calculation and then we argue that the difference is like really small. It's something divided by 2, but it's 3k by 2.
So it seems like it should be uniform between the two and also carrying the number of carry from the previous round that's effective at all.
Right, so let's draw the figures. So if let's call this t, so q minus 1 0. So if t is equal to 1, then it's always 0, 1. If t is equal to 1, that's the interval 0 to 2. If t is equal to 2, then it will look like this. Which means it's half probability 0 and half probability 1. If t is equal to 3, it's a weird shape. It's something like which is again like equal to it should be more likely to be 0. All right, so the problem is this. So if t is equal to 1, there's a clear t equal to 1 that's not even interesting. When t equals to 2, which is the case when k is 3, the distribution of the carry vector mod 2 is uniform. So it really doesn't help us. When t equals to 3, it helps us. When t equals to 4, it doesn't help us again. And it's a bit annoying that way. So what Green did, or at least what we believe we had in mind when we did this changes, is to actually let each of these real numbers be between -0.5 and 0.5, which is the same as writing your number in a base Q representation, where the entries are between -q/2 and q. And then the question essentially, if there's no carry, then you stay between -0.5 and 0.5. Otherwise, you will be between. In this case, the carry vector mod 2 is 0. In this case, the carry vector mod 2 is 1. I think it's, yeah, if you think about it, it makes complete sense. You're between -q/2 and q/2, no carry is happening. when a carry has happened, you're releasing the world, you get carried again. That happens.
Would that change anything?
Yeah, so that changes everything. After the we have -1 to 1. Initially, there's always a benefit. And yeah. After that, the distribution becomes something like this. Then it becomes flatter and flatter, but there's always a benefit to being in this region. Oh. Which is exactly what the carry vector is.
Now, do carries affect other carries?
Carries do affect other carries, but you can. So that would be another reason why this is not exactly the same as this. Carry affecting other carries and be pushed into this.
Oh, so for the first carry, you do these kinds of regions, for the second carry, you redistribute where it is.
No, you don't redistribute. You continue with the same flow. No, I meant real numbers versus discrete.
Oh, sure, that part.
Right. But then you can also push the carry and affecting other carries into this because the carry is at most k. Yeah, k is much smaller than 2, which means it can affect it by only one more. And if you're affecting it by only one more in the real in the continuous setting, that's not affected. Okay. Okay. I mean, even if right, so at least here the distribution of the carry vector in 1, 2 is non-uniform. So it is more likely that all the entries are 0 in the carry vector than any specific other setting. We still don't know how to use that yet. I haven't explained how we can use that, but at least that holds. Now that S is a such a possible setting would be 1 to be k minus 1, such that the carry vector is so it turns out that the size of S or the density of S in all possible strings for the size of S is at least q to the d times 2 to the minus d times 1 minus some small constant. That depends on k.
As opposed to what you would expect, because uniform should use it to minus.
Exactly. If it was all uniform, you get exactly 2 to the minus d, which is why this d is anything, even in an encoding. But now, in an encoding sense, it's easier to communicate, but we're not actually. It's not a distribution of upper bound. We want the upper bound for all inputs.
Can't you just set if d times 1 minus epsilon is much. Sorry, epsilon times d is much bigger than 1. Then you can just send a bit saying what you're asking first, right?
Yes, but then how do we deal with everything else? Yes.
Okay. So so that would save you in the case that you're in S.
That would say it's
Right. Okay, yeah, we're still stuck.
okay. Now it's the final element. Right, q to the d. Now it's S union S plus shift. So you shift your set S, by which I mean just every element and then gets translated by some number of shifts. And you take enough shifts such that you actually cover all of utility. And now you use the probabilistic method to say that the number of shifts needed is not that much. R is the number of shifts. So by probabilistic method, R can be due to the basically plus some small order terms. We can go to that proof in a bit if you want, but let's finish the reason assuming this. All right. Player K can see all of this. V1 to V one. So player K can also, yeah. So suppose you have an input, so this should not be, so this should be Q to the D to the n minus 1. Right, because each S is really K minus 1 vector. Each element of S is actually K minus 1 vectors, each vector in Q to the D. K minus 1. Right. So given any input in here, player K can instantly find out which of the shifts does it lie in. And suppose you have a specific input V1 to the dk, which does not lie in S, but it lies in S plus delta I. And then player K just communicates I. And with that I, every player is going to shift their inputs by delta I, so that their final inputs actually have the carry vector of zeros. And the player K does not need to communicate the carry vector at all. You already know that the carry vector is also zeros. And this delta I is a vector, but since we're reducing it to exactly n, you can put in the delta I over here to make sure that this plus delta I is equal to this plus delta I.
The variable is n x delta I
Yes.
and x.
And so William and Friedman basically they did an encoding trick, and they realized that it doesn't have to be an encoding that you're actually sending. You actually send the shift because the encoding trick guarantees that the average encoding is small. So this really comes from William and Friedman. They're using this to ensure that. So we only use it to ensure that this is a non-uniform, but then the same trick ensure that all the following ones are non-uniform as well. So that was really we used both of them together. You know the best thing about this? Epsilon k becomes worse as the k increases, even though you're sharing more and more information. What you're gaining as the constant is becoming worse because it's becoming more flat. So after all that work, we don't even have a better improvement as k increases. And it's exponentially decreasing in k. So the part that Morgan put was the epsilon k. So we looked on the online encyclopedia of integer sequences and figured out what epsilon k should be as a formula. But we couldn't prove it until Morgan did do it, just really old books and figure out what it was. What are the major doubts? We start with the major doubts.
If someone K is worse. Shouldn't. Is it? Can you group players up? So that they're solving a lower version of K, or like reducing for a lower version of K. But I guess you have to pay for each group by that.
I see, so that is correct. So you've improved it for all K, but the improvement versus ranking, but the improvement is worse for larger things.
But this is an improvement only in this like that, if you make it go overall. Like if you distribute it so that everything's optimized, what you get is basically the same thing times 1 technically.
So it gets even worse.
So if it's numbering the forehead exactly, and then it's not equivalent to numbering hand.
Should this be done?
It's not equivalent, so there's no reduction to it.
Yeah, so proving lower bounds for number on varieties at the end is in fact our main motivation to prove an upper bound. Like it's like we want to prove a lower bound, but first we should figure out what number on variety can do so that we can prove a lower bound against it. But putting a lower bound against this has like a lot of interesting implications in complexity. One thing is that it was a prime candidate to show separation between deterministic and randomized number on product complexity. We know there's a separation by counting argument, but we didn't know that explicit function. But like 2 months ago, the first explicit separation for number on forehead was shown, but it didn't use exactly n. And interestingly, like the methods used for that lower bound have huge similarity with the methods used for the breakthrough Raghu and Meka and Kelly work for the 3AP lower bound. And it's by it's Meka, Kelly, and Lovett who proved the separation on the various. They use similar techniques. And they say the problem with, so they prove the lower bound separating randomized and deterministic for 3 players. And they don't know how to extend it to like the separation for 4 players. And they say that the problems there are very similar to the problems to showing lower bounds for 4 players. So there's some really nice strategy going on with the lower bound segments.
Can you see any way potentially forward of saying the number one forward as well? I was joking earlier about, some degree 1 version of exactly n versus more, but is there like, can you you've turned exactly n into so many of these other kinds of problems, although most of them are number n. Is it potential that there is some kind of degree bounded? If there is some, or maybe not degree, but some kind of mapping from exactly into a problem that can be scaled up.
I mean, there's the possibility idea. And for all that we've explored, we don't feel like we've explored it.
I mean, what would happen if you could replace every D 2D, 4D? I mean, forget the 1 minus epsilon for the moment. Let's say you replace those all with D. What would you get?
I don't think it would improve this asymptotics. So this order k over here contains the k log k. And I think you might get rid of that.
And then getting the one minus epsilon group and you kind of already, so that would be in the root.
1 minus.
The one minus epsilon k.
No, this is adding to the order and multiplying to the order. It's not.
Oh, that's not in the,
No, it's
that's
not.
not in the radical. I see.
Well, I think the 1 minus epsilon k was in the radical. We pulled it out because it's the constant improvement, and that's why they're divided by log k in the log k. So I think, yeah, 1 minus epsilon by itself in the radical is an accurate way. They are.
Oh, no, I meant in the, you know, the.
Oh,
functions.
actually.
Yeah.
Oh,
No,
okay. We love accurate work better. That's one of the reasons we're interested in seeing, what happens between multiples of two. That could potentially give us an improvement for some k in the radical.
What was that other function which, the separation is in?
In the separation, like what function the base? It's actually pretty simple. So, there's 3 layers. Each layer gets n3 and some prime into power. Yeah. So a vector, a D-length vector, each n3 and n3. That's what x and y and z belong. Then you can compute x and y in linear parts, and layer 3 can compute this by themselves. Layer 2 can, layer 1 can compute this, layer 2 can compute this. Right? And they want to know whether all 3 are equal. In the randomized model, that actually reduces equality because each of this actually belongs to one of the layers, and they want to find out equality from the other level. Randomized model, it's hard.
It's hard to prove that it's hard.
Yeah, it's a Well, I was noting down the sessions. I was noting down the sessions that we'll see in the game, but. The board work wasn't too good all over the place, but
pretty good for one board. With like 5 things.